let me start with this. Okay. So first of all, I want to. Today's talk is about gradient boosting, and actually, Alex just mentioned about deep learning, and at the end, I mean, it is related somewhat to deep learning in the conclusion slide. So the thing, okay, started very early, okay, from Bernard Widrow, okay. So I start talking about this gradient, okay. The whole thing is, the idea is using gradient descent, okay, rather than using a matrix kind of operation. And Bernard Widrow, okay, who is a Stanford colleague, okay, and electrical engineering, he introduced this idea, and Hoff was his student. He introduced this LMS, or least mean squares algorithm, for fast online updating of the minimum variance filter, which is basically a gradient descent method. And here, I mean, for a stochastic regression model, okay, like xt being a, is ft minus 1 measurable, okay, depending, and then you have id errors. So the least squares estimate, okay, can be has this recursive form, okay, which is related to the Kalman filter. And now the LMS, so that's the recursive form, okay, so of the recursive least squares. And now the LMS recursions are just, basically, the LMS recursions basically take, let me do this. Okay, basically replace here the matrix gain. Okay, this is a gain matrix. Okay, so it takes replaces it by the scalar gain. Okay, so it's gamma t, and gamma t. Okay, depending. Okay, that's the learning rate or the gradient descent rate. Okay, is being constant, or basically, or this normalized. Okay, by taking the inverse of the sum of squares, the norm of the 6i square. And if you think of this is in recursive least squares, actually this gamma t is this covariance matrix, xi transpose inverse. Okay, so basically just taking, instead of taking the matrix, you use this. So, so this is the both batch now. So here is it started out with as a recursive algorithm. So I think Widrow is sort of doing echo cancellation for that. So it's an online algorithm. But now here this has evolved this gradient descent. From this from the recursive. Okay, you sort of do it in batches, batch learning for faster and more stable descent. Okay, and so the updates occur after batches. Okay, in other words, you don't update. Okay, at every time. Okay, and then you collect enough data and then you do the update. So this is particularly relevant. So today when we talk about big data, so you have this theta t. But that was the first idea. So now here what we want to talk about is this. There is this period. Okay, between 1997 to 2002. Okay. So where the AdaBoost, okay, adaptive boosting and gradient boosting came about. And Freund and Schapire introduced the AdaBoost algorithm, which suitably combines weak learners. So the idea of this is for classification. So you have, a relatively simple and not functioning very well with classifiers. But now, if you combine them, and then weak learners from training data in some way, okay, you can perform much better. And then it led to this. This classifier, okay, from classifier, then you go to regression and hasty. So this so Freund and Schapire were Bell Labs, and then Trevor Hasty and Rob Tibshirani. Sort of introduced additive logistic regression. And then another Stanford colleague, Jerry Friedman, 2001. So he proposed this so-called gradient boosting machine, And that's, I mean, which I'm going to talk about his algorithm to function estimation, and which is motivated by applications to trees and other additive models. So here, so basically, so before I talk about Friedman's algorithm, so I want to sort of bring in an intercept, okay, because that's related when we talk about regression. So you have a consider regression function f that has an additive. So basically, I mean, you think of it as an additive expansion, okay, and this is high dimensional nonlinear regression. And when you and here when you're talking about trees and so on, so I mean there is this or neural networks, then there is this nonlinear term. So you have this basis expansion, and the basis has a nonlinear b, okay, here, and then you have the summation beta k. So that you can think of as a basis expansion, and that involves a nonlinear parameter vector. And it is linearly associated with the regression coefficients because it's just an expansion of this type. So the observed data are xt, yt, and you have a loss function, okay, and lyt, and it is used to fit the model. And it is high dimensional, I mean, if you have a lot of bases here, I mean, p is bigger than n. So the choice of L, okay, is you have square error, okay, that's what we usually do when we talk about least squares, or the, today, Narrowdin this morning had talked about different loss functions, okay, I mean, like the Huber loss, okay, that he mentioned, okay, for M estimators, and you have absolute error loss, okay, he also mentioned that, or you have a logistic regression, okay, so of this type, okay. So that's the framework. And then now here is Friedman's gradient boosting algorithm. So the algorithm, okay, represents a generalization that connects stage-wise additive expansion to steepest descent minimization. So basically, I mean, it does this, okay. So now so-called boosting is that we start with a very simple expansion, and then we just add on. So you boost by adding, okay, by just adding more and more expansion. So I mean, so now here, and actually what is important here, I mean, so this is you want, okay, every time it chooses, I mean, these bases, okay, so now you have f hat, okay, the new function, okay, that comes in, okay, and you want it to be, let's know a step B, okay, so step B is really the thing. I mean, now every time I want to add a new, I mean, basis into it, and I do it in a greedy manner. So here these are greedy algorithms, so greedy in the sense, in this sense. So I want it to match the gradient, okay, because for it to be as correlated, I mean, so this ut is, you look at this, there's this loss, okay. So L is the loss, okay. And the law L, yt, ft minus 1, so that's the previous fk hat, okay, that's the kth iteration. So that's the previous one. And I want to take here, I mean, for it to match in the right direction, okay. So the best, you can think of it as most correlated as possible to this one. So you have, and now you choose, I mean, so here you choose this beta. I mean, so you have different. So now I'm putting in this function b. Okay, so the b will be the one that is in the most aggressive way, and now so I've chosen this b. Okay, here in this six, you get in the most aggressive in a greedy way, And then you're now having done that, okay, you want to minimize the loss next, okay, is you do this beta k hat. So, I mean, so this is basically, I mean, this gradient boosting algorithm or the steepest descent, okay, idea that he introduced. And he basically thinks of this in terms, okay, his rationale just looking at is, I mean, he thinks of gradient descent in function space. So that's why he differentiates this with respect to f. Okay, so f is the current. Okay, so you have the loss given f. Okay, so here is what he takes. So so that's the point, and then he outputs this f hat. So now there is this so related to, I mean, so there is. So something, I mean, related to shrinkage, okay, that we talk about, that we saw in earlier talks today. So a shrinkage factor called the learning rate. So now sometimes instead of being completely too greedy, I mean, you can now take smaller steps first. So that's the basic idea. Okay. So, so now I sort of in this so in Friedman's model, okay, so maybe I'll just go back. When Friedman's model, when he formulated this, okay, f does, so every time you're just adding in phi, so in his model there's no alpha. But the reason I sort of bring in an alpha is, I mean, I want to relate it later with linear regression better. So here you assume the more general model that has an intercept term alpha, and actually in Friedman's model, okay, there is also another thing, because I did not use phi k. So in Friedman originally, I mean, so maybe let me be clear here. So in Friedman, there is no alpha in his original formulation, and this phi is just a single function. Okay, there is no k. Okay, so what he was choosing was about this bk. But now, what happened to relate it better to regression? Okay, to linear regression that has subsequently been studied. So we would include an intercept term. Okay, so in fact the algorithm may just goes the same way. And then you have more general loss from, so you center, okay, for this x by xt minus x bar, and then we modify this algorithm in this way. Okay, so that's what, so basically the same idea, except I have this intercept term, and I just basically repeat. So now you can see here, this is what I mean by greedy. You want this to be this u, okay, is the same u, the derivative with respect to f, and then you have this quantity. So, so the linear case, the reason I sort of introduced this is if you have square error, and then and actually this algorithm, okay, has been the special case of this. I mean, has been looked at. I mean. And this reduces to, so you have considered this, and also, so you have square error, and then, and now basically you have beta transpose, and what I should say, there's no b here. So I say for this loss function, and without also this b, and then you just have phi jx. Okay, so this is really reduces to what is called the matching pursuit, okay, of Mallet and Zhang, and for this special case of time frequency dictionaries. And also, so this Temlyakov, I mean, that I will refer to in a moment, called this the pure greedy algorithm. And this has been also called the L2 boosting by Buhlmann and Yu. So, Buhlmann and Yu actually, so what about convergence results, okay, for this procedure? And we look at, in the special case of linear regression, it has been analyzed. And Buhlmann and Yu studied the bias variance trade-off as the number m of iterations. So, So now you see here you keep iterating. You keep iterating this algorithm, okay, and you do it until m, okay. And now notice one of the things is that you have this function, okay, phi j, and now the next time, okay, because you are just iterating out of this, I mean, this phi, okay, may be chosen again with, I mean, so at time 1, okay, at the first time I may chosen, I mean, this I may have chosen. You at this I may have chosen this basis function, okay, phi, let's say j1. Now then, at another time, okay, as I iterate further, I may choose this j1, this same function again, but then I may end up with another coefficient beta and another b. So that is the thing, okay, here. So that's now here if you look at the linear case, then you can see some of the issues, some of the convergence points. So now here, if we think of it, just think of linear regression. In the case of linear regression, so in linear regression, I mean you have this, just think of the very simple model y t is equal to beta transpose xt plus epsilon. Okay, so that's the, and then you have alpha plus beta transpose xt plus epsilon t. So that's the linear regression model, okay, which is so here, and that's what Billman and you sort of studied, and they prove convergence, okay, in this if you do gradient boosting, okay, this gradient boosting, I mean matching pursuit, then I mean actually does this algorithm converges. I mean if, okay, I mean as n tends to infinity, the sample size tends to, but now there is this subtle point is how should m be chosen. M should be chosen, I mean relative to n, okay, and actually if you choose m sufficiently, I mean in some way, or actually it is more an existence proof that there exists, I mean m sub n, I mean so that this thing converges. And that's, I mean, so here Billman particularly, I mean, refines this argument, and now here you have AP can be bigger than n, okay, I mean even at goes exponentially, I mean big O of n of to the c, and c between 0 and 1. And it shows that for linear regression, the conditional mean squared error, I mean, so which is, here you take a, so what you have, now at the end of the day, you want to estimate, okay, this FM hat, okay, which is just your fitted, successively fitted model, okay, up to after m iterations, okay. So this is FM hat, and here this is the actual function. So and now you take another, so this is the data x1 to y1 to yn, okay, so that's the fitted value. And now if we take a future x, okay, which has the same distribution, so here they talk about the ID case, so you take a future x from this distribution, and now so the mean square of this goes to 0 if m equal to mn sufficiently slowly. But that's not, so here is this point, but the result is, okay, does not provide, I mean, how slowly mn should grow. So it's widely recognized that early termination can avoid overfitting, and some variable schemes such as AIC and so on have been proposed, I mean, to choose mn in practice, but there is a definitive theory of how mn should be chosen is lacking. So that's what prompted me to look at this problem. So there is actually what I sort of look at was, I mean, now if you are doing, so I started out talking about the gradient method. I talked about Widrow, and I talked about the Kalman filter. So that's So now here I want to relate them. So if, I mean, of course, I mean, this is, I'm not doing recursive, I'm doing in a batch here. I give you this training data. You can think of it this way. So now if you, in the linear regression case, if you sort of do least squares, I mean, that's what typically one will do. So now if your P, here the big problem is P is bigger than N, so that is very hard to do. I mean, so basically you, you just cannot run least square directly. So there have been various regularization methods like L1 regularization or L2, I mean, so that's the Lasso, or the L2 is the ridge regression. So that's one way. And actually another way, okay, that has also been proposed, and is what is called the orthogonal greedy algorithm, okay, or orthogonal matching pursuit. In other words, when we add a variable, okay, this in, okay, then I mean, in fact, what we are adding, just like forward stepwise regression, when we do forward stepwise regression, every time we add a variable, it is orthogonal, I mean, to whatever, I mean, I sort of orthogonalize things and I add something that is orthogonal to it. So, but orthogonal matching pursuit is because I don't have to orthogonalize all the covariates. I mean, so essentially, this is so I mean a variant, okay, or a speed up version of forward stepwise. So here, and actually, again, I emphasize that the choice of the variable. Notice in all of this is greedy. Okay, you add the one, okay, that gives you the most reduction in the residual sum of squares. So there's a definitive convergence theory for the orthogonal greedy algorithm, and which is also so here, and a major difference between OGA and PGA is that so PGA is the pure greedy, okay, which is or the matching pursuit, or the one gradient boosting, okay, that we talked about before. So is that at each iteration, OJ selects a new input variable, and PJ can select the same input variable in multiple iterations. So for OGA, sort of Ing and myself, okay, have been able to show that there is an optimal bias variance trade-off. Okay, so in other words, how many iterations should be come in? Okay. So there, when we think of OGA, I mean, it is pretty clear. I mean, you have a sample size n, and how many variables, okay, of course, we assume, okay, underline there's a sparse model. So how many variables, okay, should you include, okay, in this? And then, so there, I mean, you can look at bias. If you include too few, then, I mean, there is bias. If you include too many, okay, then, I mean, you may create a very big variance. So there's a bias variance trade-off, okay, which is what, I mean, what Bullman and so on have anticipated, but there was no definitive answer as to how MN should be chosen. But in the case of OGA, it was actually quite clear, I mean, how it should be chosen. And then we find that MN should be of this order. So central to the derivation of this optimal convergence rate is what, I mean, turns out, okay, but which makes this, we have the same, basically we can use similar insights when we go to this OGA that uses the same forward stepwise variable selection procedure but assumes the corresponding regression parameters to be known. So I will come back to this. So there is essentially how we analyze this is that there is, I mean, so basically, I mean, that's the choice of how many, I mean, variables should come in, which also corresponds to how many iterations you should do. And now you put in this number of iterations, okay, then I mean, you enter these many variables, And now then the next thing is to compare if you knew the parameters for these selected variables. So this is what is called the semi-population version. So if I look at this, how well, okay, if I want to estimate yx is the true regression function, and now the oracle tells me the actual parameters of my chosen one, so this is, let me call it y tilde x, okay. So I've chosen m of this, so this is y tilde mx. But now actually what I have finally chosen, my sample has chosen y hat mx, okay, that's the OGA algorithm. So the whole thing is to compare y hat to the semi-population part, okay, that is when you know the parameters for your selected value, and then compare this y hat to the y tilde. So that was the basis of our analysis. But now here that suggests a way out, okay, I mean, so inspired by OGA for high-dimensional regression, we have developed a modified gradient boosting, because gradient boosting actually turns out, okay, I have mentioned, even in the linear regression case, I mean, the number of iterations, okay, I mean, there's this convergence problem, okay, it has been shown, even in the linear case, that you will converge. I mean, if your iterations, okay, I mean, don't stop, okay, I mean, you take early termination, so to speak, I mean, correctly, then, I mean, you will converge. But there has been no guidance, okay, about how, I mean, although there, I mean, have been suggestions, but there's no theory about how, I mean, how many iterations we should do. And now, in fact, this modified, I mean, gradient boosting is basically, I mean, there are two ideas here. One idea is that if you think of OGA, okay, now OGA, the thing is very clear because the iterations are just the number of variables. I mean, they come into a regression. So and now actually we say we cannot, I mean, get in too many variables. There will be overfitting, and there will be all kinds of issues. Okay, so here we basically decouple the problem. So essentially, I mean, we will be now. Here is the formulation of the greedy part. So so here for k from 1 to m, okay, so this is the modification is we choose the so that's the so let me make this clear. So what happens? In fact, unfortunately, yeah, this slide I should yeah. So so this modified greedy boosting is basically like this. So here, I mean, so essentially, we choose the variables. Okay, we give some sort of leeway. I mean, in other words, I do not have, if epsilon n equal to 1. Okay, I mean, actually, I can formulate this. I mean, this part. Okay, is find the one that is most correlated. Okay. Well, I shouldn't use the word correlated because after all is in the analysis is the inner product of this. So I find the one that is most after I normalize. Notice the phi j I normalize by, I mean, is sum of squares. Okay, I mean, take the norm. Okay, so to speak. And here I will choose the j. Okay, first of all is I will choose the j that is most related to that. Okay, so this is the part I will now choose these variables, and I will do this. Okay, I will only choose it up to m. Okay, so basically, so that's the so this is the algorithm, but but now actually, and after I only, I do this up to m, okay, so unfortunately, I think when I was, this slide, okay, was somewhat cut short because actually it's longer than that. But, so what happens is after m, so there is m, I let m in, okay, so that's what I will be doing. But then I didn't say that it's after m, so there is m up to m tilde, okay, something that is what was cut short. And so I choose this set jm hat. But then after this jm hat, let me see if, yeah, after jm hat, so then, I mean, so this j and j tilde are chosen in this way. But then after jm hat, okay, then I still continue iterating. I mean, I'm not finished, so that was the part that was, I mean, that was cut, okay, in this in the slide. So after jm hat, okay, I've selected this set of variables, and I still keep on iterating, okay, m is the first, but now I'm not adding more input variables. I will now still keep on iterating until I go to m tilde, okay. So m tilde is for the selected variables. I will still be doing gradient boosting in that way. So the basic idea can be thought of in the following way, because we are doing, there's this nonlinearity going on, okay. So we are minimizing this loss function with gradient, okay. So there are two issues. One is, I mean, have you enter enough variables. The other is, even I've entered enough variables. So suppose, I mean, I just have a fixed set of variables. Okay, there's no variable selection. Now I'm just doing, I want to maximize, I want to minimize the loss. Okay, so now I'm doing gradient search for the minimum. So you still, I mean, have to keep on iterating, okay, until you go to the minimum. So basically, I mean, in this in the second part of that pseudocode, I mean that's from m to m. There is actually, after I've selected m variables, then I still keep on iterating until until my thing goes to tolerance. So this is what I say. With a specified, I mean, tolerance for convergence, modify MGB terminates when the loss is minimized within the tolerance limits. So that is basically this idea. Okay, so now I better hurry up. So so this simulation study, okay, shows, I mean, now if you just do simple gradient boosting, okay, then I mean with some, I mean, just some termination rule, okay, very big, okay, here, then, I mean, you get a, now, if you do gradient boosting, okay, with k-fold cross-validation, so this is, I mean, actually, you can cut it down substantially for this example, and now, actually, if you just automatically do this, modify gradient boosting, then you sort of do considerably better. Okay, so that is the basic, so to finish up, the basic idea about this OGA, I mean, for linear regression, as I said, I mean, we have this convergence rate, okay. I mean, so in the paper with Ng, okay, I mean, that was what we proved. Now, essentially, we try to do similar, we try to do similar things, okay, to imitate that theory. I mean, and now what happens is, I mentioned about the semi-population version of OGA, and in fact, in this case, okay, we can also we also have, I mean, a similar theory, okay, I mean, similar semi-population model. So this is really by going through this semi-population model, then we can, I mean, with actually much more work, we can, so we can formulate, I mean, so the thing is, we can formulate this semi-population model, and actually for we also use Temlyakov as a bound for orthogonal greedy algorithm. Now, actually, it turns out he also has a similar bound, has another bound for this pure greedy algorithm of what is gradient boosting. So here, I just mentioned his bound. And so the bound is that basically that's where related to when I talk about those inner products. So that's related, I talk about convergences, okay, for the normalized phi. So here, the input is the phi. So so here you have a set, okay. So you have H is a Hilbert space, okay, within a product, okay. And then D is a dictionary, okay. It's called a dictionary if H is the closure of the span of D, and also every element of D has norm 1. And this set ADM is just F, in H, okay. And F is, has this expansion, okay, CK, psi K, and then and psi K in the dictionary, and here is this. So the point is, if I have F, anything that has this admits this infinite dimensional expansion, then I do a greedy algorithm, okay, weak greedy orthogonal, weak greedy algorithm. In other words, here I do not need, when Tm is equal to 1, that is the greedy, okay, the greedy algorithm, okay. So here, you want to find the one that is most correlated to that, okay, but now that has the largest inner product to this. But now here you have you allow yourself some leeway, okay, so that's the Tm, and then there's this bound, okay, F minus this Gm Fd is bounded by that, okay. So let me, I think I sort of finish up quickly. So here this kind of things that has been looked at by, for example, by Smale and Zhou, okay, and also Yao, also from Steve Smale's group, and all these. So they actually talk about early stopping regularization for gradient descent learning. And so the issue is, when do you stop? Okay, so we introduce a new approach to address this issue, which becomes particularly difficult for high-dimensional nonlinear regression problems. And this approach achieves early stopping by putting an upper bound on the number of distinct basis functions that have been included in a greedy manner, and then continuous gradient boosting with these selected basis functions. Nonlinearities in the loss function and the phi jx bt are handled by successive linear approximations via the gradients. So the semi-population model that we use effectively to analyze OGA can be extended to the present setting, because it basically involves the greedy model selection rule used in the sample, but then the parameters are assumed to be known for the data-dependent selective model. So as I said, we first compare Yx to compare F, okay, this to the semi-population model, and then compare the semi-population model to this to the modified gradient boosting. And so here the basic model 1, so for this with this phi JB arises in single layer neural networks, as illustrated in the simulation study. Applications in the era of big data have led to multi-layer of deep learning networks, and gradient descent methods and the refinements, for example, backpropagation, have been used to train these networks. And Friedman, okay, has introduced the stochastic gradient boosting. And the theory we have developed, can be extended to modify stochastic gradient boosting. And more importantly, now when we talk about deep learning networks, deep learning, so essentially, people like Hinton, Benjo, LeCun, and Schmidt-Huber sort of use these learning networks, okay, this probabilistic interpretation. So we're working towards the theory of deep learning, and the associated algorithm by combining the recent advances in gradient boosting and adaptive filtering in hidden Markov models. Okay, thank you for your attention. So I think I've just use up my time. Sorry. Yes. Okay. The deep learning is actually needs much more. Okay. So because I say for the single now here single layer networks, but now when you have multi-layer, right, input and then output, then this this kind of analysis. Now because I've told you I've count on this semi-population model, because then actually if you have, I think with a couple of that I can do, but if you have so many, because now notice I do variable selection, right? Now here you have all these the networks, so the selection is a big problem. So I think that is really where these probabilistic kind, the hidden Markov modeling, right, come in. Yeah. So probably once you sort of train your network, then you can go back to do at another stage. Yeah. Okay, thank you. So I also apologize. I will correct my slides, okay, because I posted that, because it got trimmed.